Hello everybody, CozyAzeroth here, aka Zachary Fruling, and today we're going to continue our run-through of Chapter 3 of Beginner's Basic for the Texas Instruments TI-99 4A home computer. If you didn't see my run-through of Chapters 1 and 2, check those out on my YouTube channel. You can find it under CozyAzeroth or under Zachary Fruling, either one. Chapter 3 is called More Programming Power, and I've got our classic 99 emulator queued up here. So let's, before we dive into the chapter, let's get into TI Basic. So press 1 for TI Basic, and let's dive into Chapter 3. By this time, you've had quite a bit of programming experience in TI Basic. You know what a program is, how it's structured, and how it's performed by the computer. Now we're ready to add a few more techniques to your programming skills. In this chapter, we'll introduce you to several new TI Basic features. First, there's the very useful and versatile for next statement, which creates loops in programs. Next, we'll cover some plain and fancy printing using the print statement and the tab function. Then we'll add some details about the number power of your computer, the way numbers are displayed on the screen, and the order in which the computer performs mathematical calculations. Finally, we'll introduce you to the integer function, the int integer function. These new features will help you increase your programming skills, building on those we've already discussed in previous chapters. They'll also prepare the way for even more exciting things to come. The for next statement. Chapter 2 presented several examples of the go-to loop, which repeats a set of statements indefinitely or until you press clear to stop the program. The for next statement also creates a loop, but it's different from go-to in two important ways. 1. The for next statement is actually a pair of lines in the program, the for line and the next line, each with its own line number. 2. You control the number of times the loop is performed. After the loop has been executed the number of times you specify, the program moves on to the line that follows the next line. The for line has the form, and I'll read you the sample here, 30 for a equals 1, 2, 3. Not 1, 2, 3, 1, 2, 3. Variable, a is the variable, space after for and a space after the little equation here, or the variable assignment. Upper limit, so it loops from 1 to 3, and 1 is the starting count. The next line could be 80 next a, so a space after next, and then the same variable is used in the for line. These two lines would cause the portion of the program between the for and next lines to be performed 3 times. In this example, the starting value of a is 1. After each pass through the loop, a is increased by 1. Its value is then tested against the upper limit, 3 in this example. After the third pass through the loop, a is equal to 4, so the program exits or leaves the loop to the line following line 80. To help you see the differences between go-to and for next more clearly, let's compare two similar programs, one with a go-to loop and one with a for next loop. A go-to loop. Type new, press enter, then enter this program. Okay, let's do that. Let's see. There's a 10, call clear, that clears the screen. 20, let a equal 1. Let a equal 1. 30, print. Oops, 30, print. And what do we have here? A equals, and I think I saw a semicolon there. We'll double check. Yep, semicolon, then the variable a. 40. Let a equal a plus 1. So it adds 1 every time this line is encountered. And 50 go to 30. Okay, let's see what it says here. Before you run the program, think for a few minutes about what it will do. First, the initial value of the variable a will be set to 1. Then, the computer will print out the current value of a. Finally, the value of a will be increased by 1, and the program will loop back to line 30. It will go on with this procedure until you press clear. Ready to run the program? Type run and press enter to see it in action. When you're ready to stop it, press clear. Okay, let's run it. And as predicted, it just increases the value of a one at a time until the computer isn't able to handle it anymore. So let's break the program here. Okay. A for next loop. Now let's examine a similar quote counting program with a for next loop. Type new and press enter to erase the program first, then type these lines. Okay, let's erase our program. New gives us a new instance of TI basic. 10 call clear. 20 for a equals 1 to 5. 30 print, same print line essentially. 30 print a equals the value of a. 40 next a. Next a. 50 print out of loop. 60 print. Okay, this print line repeated again. Print a equals semicolon a, and 70 end. End line, of course, is not necessary, but it's included for completion's sake in a great many of these TI basic programs. Before we run it, let's see what it says to do. Think about the way this program will be performed. The value of a will start at 1 and will be increased by 1 each time the program completes line 40. As soon as the value of a is greater than 5, the program will exit the loop and continue with line 50. If we listed the lines in their order of performance along with the increasing values of a, this is what we'd have. Okay, so we have a nice little sort of, not really a flow chart, but a linear example of how this program will work. So line number 10, value of a is 0. Line 20 sets up the value limits for a and starts the loop. This is the first pass through of the loop, lines 30 and 40. Value of a goes from 1 to 2. Second pass goes from 2 to 3. Third pass goes 3 to 4. Fourth pass 4 to 5. Fifth pass 5 to 6. And once it's greater than 5, we're out of the loop. And then we get line 60 and 70. Run the program, and the screen should look like this. Okay, so we get a equals 1, a equals 2, a equals 3, a equals 4, a equals 5. Then we're out of the loop, and a equals 6. Just to demonstrate we're out of the loop. Okay, so run. Oh, incorrect statement in 60. What did I do? List. Do I have a typo? Oh, I got a double print there, didn't I? 60 print a equals. Okay, now let's run that again. Now it should work. Yeah, a equals 1, a equals 2, a equals 3, a equals 4, a equals 5. Then we're out of the loop, a equals 6, and we end the program, and we are done. Sorry about that. Didn't notice I had typed print twice, just out of habit. The following flowcharts illustrate the differences in the two programs. Okay, I'm going to zoom out a little bit so I can see the entire. Oh, what happened here? Accidentally scrolled when I. Where are you? There you are. Okay, here's our two flowcharts. So the go-to program clears the screen, sets an initial value of a, print a equals and the current value of a, increase a by 1, loop back to line 30. And in that program, the loop will continue until you press clear. In the for next program, the screen clears. We set the quote parameters for a, the beginning and ending values. Print a equals and the current value of a. Increase a by 1, check to see if the new value for a exceeds the upper limit set by line 20. If the answer is no, repeat lines 30 and 40. If yes, we break out of the loop. So the loop runs and runs and runs till the value of a exceeds the upper limit. Then we print out of loop. Then we print the current value of a, and we stop running the program. In Chapter 2, we also use the goto statement in a call color program to create a delay loop. 40 go to 40. This line caused the program to, quote, idle and hold the color design on the screen until you pressed clear. Without some sort of delay loop, the color we used in the program would have blinked on the screen only for an instant before the program stopped and the screen returned to its normal immediate mode colors. We can also use the for next statement to build a controlled time delay into a program. Consider this example. 20 for a equals 1 to 1000. 30 next a. Better still, let's try it. Type new and press enter, then type in the following program. Okay. Let's see, new. Okay, now let's type it. 10 call clear. 20 for a equals 1 to 1000. 30. Next a. And 40 end. Now this is going to take a minute because it's got to count all the way to 1000. And I think what I'm going to do, let's run it. Okay, it says now run the program. What happens on the screen? Not much really. The screen changes to a light green and the cursor disappears. After a short time delay, while the computer, quote, counts from 1 to 1000, the screen changes back to cyan, a light blue, and the cursor reappears. Okay, so light blue signals end of run. Okay, so we're going to run it, but then we're going to improve this so we can see what's actually happening behind the scenes. So let's run. And so nothing is happening here that we can see, but it counted from 1 to 1000 fairly quickly. Although no other lines are being executed between the for and next lines, time passes while the computer counts for the number of loops, in this example from 1 to 1000. The following program utilizes a for next time delay loop call in a call color program. Okay, so we can actually kind of see what happens here a little bit. Call color with a for next loop. So let's type new, press enter, and enter this program. 10 call clear. Anyone who's programmed in TI Basic knows 10 call clear is the first thing. 20 call color 277. 2,7,7. That sets the color scheme. 30 call HCHAR. And I gotta remember these numbers here. 12, 3, 42, 28. 12, 3, 42, 28. Okay, for B equals 1 to 1000. $50, next B. And 60 end. Okay, let's see what it says before we run the program. This program will print a row of asterisks on the screen. However, since the foreground color, the color of the asterisks, and the background color are both dark red, the screen will show a solid horizontal bar of dark red. The red asterisks blend into the red backgrounds. Now run the program. Does the color bar stay on the screen long enough for you to observe it carefully? If not, change line 40 to increase the time delay, 1 to 2000 for example. Suppose we want to see a bar of a different color. Let's run it before we start changing the program. Okay, so we've got our horizontal bar, red asterisks on the same red background. You can see when the program ends, the color scheme goes away and we can actually see the asterisks. Suppose we want to see a bar of a different color. We could retype line 20, inserting a new color code for the foreground and background colors. But there's an easier way to edit the program so that we won't have to retype line 20 every time we want to change colors. Type these lines. 15, input A. Okay, input A. Then we have 20, call color, 2, A, A. 2, A. And 60, go to 10. Well, a go-to loop and a for next loop in the same program. Run the program and see how it works. Remember, when you see the question mark on the screen, the program is waiting for you to, quote, input a color code from 1 through 16. If you enter a number that is outside this range, you'll see this error message on the screen. Bad value in 20. Remember also that color 1 is transparent and color 4 is the screen color in the run mode, so you won't be able to see these bars on screen. Experiment now with the color codes and change the time delay in line 40 if you want to make the bar stay on the screen longer or disappear faster. Okay, let's run it. So we can type in a color code like 13, gives us a darker green bar. We have our time delay loop, the computer's counting from 1 to 1,000. The go-to loop then circles back to the beginning of the program. So let's type in a different color code. How about 6? I think that's a blue of some sort, kind of a purpley blue. Okay, and so on and so forth. One more. How about a white one? There we go. White asterisk on a white background. And when we break the program, in fact, let's break it while the colors are still on the screen. The asterisks, excuse me, are still on the screen. Here's 9, and we're going to break it right now, and you can see the color scheme goes away, and we get our asterisks back. Okay, let's change it a little bit. Let's list the program, and we are going to change the time delay. So let's take line 40 for b equals 1. Oops. Habit equals, we've been doing too much modern programming here. B equals 1 to, let's do 1,750 rather than 2,000. So that way, behind the scenes, when the program encounters that time delay loop, the computer is going to count very quickly from 1 all the way up to 1,750. So the asterisks on the screen will stay up 75% longer than they were originally. Let's run the program. We input a color code. Let's just pick a different color, 5 this time, different color blue, and now they stay on the screen a little bit longer. Eventually the loop's going to run out, and it's going to the go-to loop will force the program back to the beginning, asking us for a new color code. Let's do magenta this time. I remember color code 14 is magenta, and there we are. Okay, let's list out the program one more time. And let's see what the book says to do next. Experiment. Here's a challenge for you. Okay, can you change the program above to make a single small square of color appear on the screen instead of a bar? Hint, see Chapter 1, pages 20 to 22. Review using HCHAR or VCHAR to display a single character. Okay, so we don't want a bar. I think what we have here, we've got in the call HCHAR statement, we have row 12, column 3, 42 right here is the character code for an asterisk, and this number right here, 28, means 28 repetitions of an asterisk. So let's edit line 30 to get a single asterisk instead of 28 asterisks. So call HCHAR 12, 3. In fact, we could change the position. Let's do 15, 7. Same thing, 42. And let's do only one instance of an asterisk. Now, when we run the program, it's going to ask us for our color code. Let's do 7. And we get only a single square, which is really an asterisk on the same color background. And then if we do the same thing again, but in the program while that's still on the screen, you'll see that will convert back into an asterisk that we can see. Okay. Nested for next loops. You've just seen that we can use both a for next loop and a go-to loop in the same program. It's also possible to use more than one for next loop, one inside another in a program. We call these nested loops. As an example, let's experiment a bit with a program very similar to the one you've just completed. But this time, we'll get a little fancier. We'll make the bar, quote, walk down the screen so that it appears in a different position each time the color changes. Type these lines. Okay, I need to undo my program here a little bit. Oh, actually, we're clearing the memory and typing a brand new program in. So let's do that. New. Okay, so 10 for a equals 1 to 16. This is the beginning of our first loop. Sets the limits for a, 1 through 16. 20, call clear. What's interesting about this instance of call clear is it's going to clear the screen every time the loop runs. Okay. 30, call color 2, A, A. 2, A. Okay, so it's basically character set 2 and then whatever color for A, 1 through 16. Both the foreground and the background color. 40, call HCHAR. Okay, 40, call HCHAR. Okay, we're going to get a little fancy. A plus 5. That's the row number. 3, this is the column number. 42, that's the character code for an asterisk. And 28, that's the number of repetitions horizontally. Okay, 50 for B equals 1 to 300. So this is the beginning of the loop inside the first loop. For, we said B, right? For B equals 1 to 300. Okay, now we have to end our loop. So we have to end the innermost loop first, which was, use the variable B. So 60, next B. Now we need to end the outer loop. So next A. So B, of course, is the time delay loop. All we're doing is creating a time delay here. You can see for B equals 1 to 300. Next B, all that does is create a time delay of 300. I don't know if they're milliseconds or however fast the computer counts from 1 to 300. Might be milliseconds, I'm not sure. 70, next A. So that changes, so this outer loop is going to loop through 16 colors, 1 through 16. This is going to change the color every time the loop executes. And finally, when that loop is done, we end the program. End. Okay. Notice that one loop is wholly contained within the other loop. That's why these are called nested loops. One is nested inside another. This program gets a lot of mileage out of the variable A. We're using it to control the number of times the program is repeated, a loop counter, to define the color codes for foreground and background, and to determine the row position of the color bar. Before you run the program, remember that color 1 is transparent and color 4 is the run mode screen color. You won't be able to see these bars. Now run the program. Does the bar appear to move down the screen? Let's do it. Okay. Run. It does appear to move down the screen. Of course, we couldn't see the one that was the same color as the run mode color. And the program ends. What happens if you shorten the time delay loop? Try changing line 50 to 50 for B equals 1 to 100. Okay, 50 for B equals 1 to 100. That will make the line, quote, walk down the screen faster. There we go. It's moving a little faster down the screen. Another interesting change would be to make the bar vertical instead of horizontal. We can do this easily by changing line 40. Type and enter this new line. Okay. 40, call VCHAR. We've got 1, so row 1, column A plus 5. Then we've got same character code, 42 for the asterisk. And we've got 24 repetitions this time. You have to shorten that up a little bit because the screen is it's wider than it is tall. Fewer characters going vertically. Let's see what happens. When you run the program this time, the bar will be vertical and will move across the screen from left to right. Okay, let's run it. There we go. We can make it go quite a bit faster if we want. Let's list out the program. Okay, how about we'll take our 4 next loop, or time delay loop on lines 50 and 60. Let's change line 50 for B equals 1 to 10, just much faster. Should go 10 times as fast. What did I do here? 70, for next error in 70. List. What did I do? Oh, I forgot to type 4. 50 for b equals 1 to 10. There we go. That should fix it. It's going to move quite a bit faster now, see? I love how easy it is to get colorful things on the screen in this system. Okay. Now let's examine another program with nested for next loops. The following program displays 64 of the alphanumeric characters, codes 32 through 95. See Appendix B for a list of the character codes, and we looked at that in a previous video, so we're not going to do that right now. Enter these lines. Okay, new. Let's get rid of our program in memory. Now let's type in a program. 10, call clear. 20, let char equals 32. So we're defining a new variable called char, and we're setting it to 32. Okay, and starting value for the variable char, in this case it's a character code, that's why it's descriptively named char. Okay, 30 for row equals 7 to 14, that's the beginning and ending values for row number. Okay, for row equals 7 to 14, so the loop will start at 7 and loop all the way through 14. Oh, I forgot to give it a line number, hello. For row equals 7 to 14. Let's list out the program here. Let's keep going. 40 for column equals 13 to 20. Equals, oh, you forget the values? 13 to 20. 20. All right. 50, call HCHAR, means we're going to set a a horizontal list of characters across the screen, starting at row number, column number, defined by those variables, and using the character code CHAR. Okay. 50, call HCHAR, row, column, and character code CHAR. 60, CHAR equals CHAR plus 1. It's going to basically increment the value of CHAR. Okay, now we need to end our loop. So we have nested loops here. We've got the loop for column inside the loop for row. So we're going to end the column loop, 70. With next column. That's why descriptive variables are so handy. There's the space there. And finally, we need to end the outer loop for the row. 80, next row. And 90, end, and the program is done. So let's look at our program. We clear the screen. We're going to create a loop that, starting with the character variable set to 32. Actually, it's not a loop, excuse me, that's just defining the variable CHAR as 32. So the character is going to stay the same, that's not changing. Now we have the beginning of the loop for row equals 7 to 14. So every time this loop runs, the value of row is going to increase by 1, 7, 8, 9, 10, all the way until it hits 14. Inside that loop, we have another loop. The column is going to change from 13 to 20, and that's going to run inside this outer loop. We're going to print the character onto the screen in a row column, and looks like only one iteration of it, one instance. Row, column, CHAR, so it's only one character. Then we're going to increment the value for the inside that loop. Actually, so now that I think about it, there isn't a separate loop for the character, but inside this inner loop, we're going to change the character value by 1. So every time the character moves, it's going to change. Then the inner loop will iterate, and then finally the outer loop will iterate as well. Okay, now let's run it and see what happens. Let's actually see what the book says it will look like. The program will look like this on the screen. Looks about right. Okay, let's run it. Actually, before we run it, let's see what the book has to say. There are several things we'd like to point out about this program. First, for next loops do not have to start counting at 1. They can begin with whatever numeric value you need to use. Second, the nested loop, for column next column, is not just a time delay loop. It actually controls a part of the program repetition. Finally, line 50 is called a wraparound line. It has more than 28 characters, so part of it prints on another line on the screen. This is an important point. Program lines can be more than one screen line long. In fact, a program line in general can be up to 4 screen lines or 112 characters in length. The exception is the data statement. See the basic reference section of the user's reference guide for an explanation. Notice that wraparound lines, that is the second, third, or fourth screen lines of a program line, are not preceded by the small prompting symbol. Run the program, and the 64 characters will be printed in nice, neat rows on the screen. Okay, let's try it. Run. We've got a bad value in 50. What do I have here? Oh, yep, I see the typo now. Row, column, we've got 2 n's in column there, so let's retype line 50. Call HC. We're going to debug our program, so to speak. Row, let's be a little more careful here. Column, and CHAR. Now let's run the program. And here we go. All of our characters being printed in nice rows and columns on the screen. Hold on, there are only 63 characters on the screen. What happened to the other one? Well, there are actually 64. Look at the top line and notice that it appears to be indented 1 space. That's because character 32 is a space. Even though a space doesn't print anything on the screen, it does occupy room on a line, and it is a character as far as the computer is concerned. Experiment. Okay, let's add to the character program above. Enter these lines. Add color to the character program above. So let's add another loop here. See, we're adding a loop inside of the loop. For I equals 1 to 8, so on 22, well, I equals 1 to, did it say 8? 8, yes. To 8. Line 24, call color. So we're going to change the color scheme every iteration here. I, 7, and 15. So this is basically looping through the 8 character groupings. And then we're going to use the foreground color number 7 and the background color number 15. I think the background color 15 is gray if memory serves, and 7 is either a red or a blue. I can't remember which. And then we're going to have next I that completes this little tiny loop inside of the loop inside of the loop. Next I. Try other color combinations until you find your favorite. Okay, let's run it. It was red. So gray background. What's interesting about this is basically it's looping before it ever prints anything onto the screen, and so it's basically coloring all 8 character groups 1 through 8, one at a time, before anything ever prints on the screen. So by the time it prints something on the screen, all of the 8 character groups have been defined using this color scheme. Try other color combinations until you find your favorite. Well, let's list out the program. Yeah, you can see before the row, the nested loops, the 4 next loops, we have one for the row, one for the column here. Before those ever happen, we get this small little loop that runs through the 8 color groups, setting them all to this color scheme. So let's try a different color scheme. 24. I'll use one I used to use all the time. Call color. We want I, of course. That's the variable in question. Foreground. Let's do 16. And background 13, that's white on a darker green screen, if memory serves. I like the contrast level with that scheme. Okay. Error conditions with for next. We mentioned earlier that a nested loop must be completely contained within another loop. If your program included lines like these, okay, let's look at this. 20 for a equals 1 to 6, that defines a loop. We have a loop inside of a loop, 30 for x equals 5 to 10. Now here's the problem here. We need to end the inner loop before we can end the outer loop. So lines 80 and 90 are either reversed or would give an error message. The computer would stop the program and give you this error message. Can't do that in 90. The computer can't go back inside the completed A loop to pick up the beginning of the X loop. We could try it. Let's sort of make sure we're done with the program we just typed in. It looks like we are. Let's try this little program that would generate an error message. So let's clear our memory, and let's start typing in a program. 20 for a equals 1 to 6. Then we have line 30 for x equals 5 to 10. Now we're going to create our lines of code that will generate the error message. 80, next A. So don't model what I'm doing here. This is purposely wrong. Next A. And 90, next X. So we are going to get an error message. Can't do that in 90 as predicted, because we need to end the X is the inner, the loop containing the variable X is the inner loop, so we need to end X before we end the outer loop A. Okay. Another possible error condition with for next statements is accidentally omitting either the for line or the next line. For example, if you attempted to run this program, let's type it in. New 10 for a equals 1 to 5. Print A, and 30 end. Okay, let's see what it says will happen. We can probably guess here. So for a equals 1 to 5, so the computer's going to define a variable. It's going to be used for a loop. It's going to start it with a value of 1. Then it's going to print A, so it should print 1 successfully on the screen. It's going to, unfortunately, we're missing the line that says next A to send the program back to line 10 to complete the loop, in other words. Then we end the program. So we're going to get an error message that there is no end statement. Or excuse me, a next statement for this loop. For next error, exactly. As predicted. If you encounter an error message, just list the program, type list and press enter, identify the error, and correct the problem line or lines. Let's fix this program now. So we'll list out the program. So what we're missing is the end of the loop. So let's type line 25 next A. And now A will loop from 1 to 5, printing the value of A at every iteration of the loop. So run 1, 2, 3, 4, 5, and the program ends. Done. Program. We have debugged our 3-line program. We've given you quite a lot of information now about for next loops, so it's probably time for a change of pace. Let's review a bit of the print material we covered in Chapter 1. Plain and fancy printing. While using the print statement in the immediate mode, we saw that a difference in spacing occurred when we used a comma or a semicolon to separate numeric values in a print statement. Let's take another look at this. Spacing with commas. Try each of the following examples, and each will assume that the screen has been cleared by typing call clear and pressing enter. Okay, let's just type new, get a new instance of TI-Basic. Let's type call clear. Okay, type this and press enter. Print 1, 2. 1, 2. It's going to print 1 and 2 in separate columns on the screen. The screen has been divided into 2 regions now. Okay, print 1, 2, 3, 4, 5, 6. Okay, separated by commas. Print, actually let's call clear. Print 1, 2, 3, 4, 5, 6. And so basically what's happening, it's printing 1, moving to the second half of the screen, printing 2, then going back to the first half of the screen, printing 3, second half of the screen, printing 4, so on and so forth. That's what's happening there. So far, we have used only small positive integers. Let's try some simple negative numbers. Okay, so call clear. This is all immediate mode. This is not a program per se. Print -1, -2. -1, -2. -1 and -2 in the 2 columns on the screen, invisible columns. Now let's try a combination of positive and negative numbers. Okay, 1, 2, -3, -4. Okay. Print 1, 2, -3, -4 separated by commas. So 1 in the first column, 2 in the second column. -3 back to the first column, -4 back to the second column. Note that the computer always leaves a space preceding the number for the sign of the number. For positive numbers, the plus sign is assumed and is not printed on the screen. For negative numbers, the computer prints a minus sign before the number. We mentioned in Chapter 1 that there are two, quote, print zones on the screen line. Each print zone has room for 14 characters per line. And you can see a little graphic here, kind of two invisible columns. This book is calling them print zones, but column 1, column 2. Print zone 1 is spaces 1 through 14. Print zone 2 is 15 through 28. When you use a comma to separate numeric values or variables in a print statement, the computer is instructed to print only one value in each zone. Therefore, since there are only 2 print zones on each line, the computer can print a maximum of 2 values per screen line. If the print statement has more than 2 items, the computer simply continues on the next screen line until all items have been printed. Now let's try some examples with string variables using commas as, quote, separators. See page 35 of Chapter 2 if you need to review string variables. We did that in a previous video, so we're not going to do that right now. Okay, let's just type new, get a new instance of TI Basic here. Let a string equal, quote, zone 1. A string, $, equal zone 1. Okay, let b string equal zone 2. Okay, we basically just defined 2 different string variables. The computer is storing those values in memory. We're going to print a string, comma b string. So we're going to take these values we just defined, zone 1 and zone 2, and we're going to print them in the 2 different printing zones or columns on the screen. So a string, or zone 1, will be on the left, b string, or zone 2, will be on the right. And that's what we end up with. Kind of left aligned within each column. The strings, the letters and numbers within the quotation marks, are also printed in different zones on the screen when a comma is used to separate the string variables. Try this example. Okay. Again, I don't need to do this because we're basically rewriting these variables, but we're going to clear the computer's memory first. Okay, let a string equal 1. Let a string equal, written out now, not a numeric variable, but a string variable, 1, the word 1. Let b string equal 2, basically b, c, and d, 2, 3, and 4. Okay, so let b string equal 2. Oh, I forgot a beginning quotes. Let b string equal 2. That works better. Let c string equal, quote, don't forget the quotes, 3. Let d string equal, quote, 4. Okay, let's see what it says to do next. Print a string, b string, c string, and d string. 1, 2, 3, 4. Print a string, comma b string, comma c string, comma d string. So as predicted, what's going to happen here, we're going to have a string printed on the left side of the screen, that's 1, b string on the right side of the screen, 2. Then it's going to loop back to, or kind of move back to the left side of the screen. That's what the comma does, kind of tabs you over to the next column, but there is no column, so it goes back to the, and you got to remember the BASIC was originally programmed for hard copy, so it's thinking of printing as if it's printing on a piece of paper. That's why you get some of this weirdness with the columns and the print statements. C string is going to be on the left, D string is going to be on the right. 1, 2, 3, 4, and that should match what we see in the book, and it does. Note that for strings, the computer does not leave a preceding space. Okay, spacing with semicolons. Now let's look at semicolon spacing. Try these examples. Okay, print 1, semicolon 2. Let's clear the screen. Print 1, semicolon 2. Aha, the numbers are much closer together. Okay, print 1, semicolon 2, semicolon 3. One, 2, 3. You can see the difference there. The semicolon instructs the computer not to leave any spaces between the values or variables in the print statement. Then why do we see spaces between the numbers on the screen? Two reasons. First, remember that each number is preceded by a space for its sign. Second, every number is followed by a trailing space. The trailing space is there to guarantee a space between all numbers, even negative ones. The way numbers are displayed is discussed in detail in Appendix D. Let's scroll down and look at Appendix D really quick. Then we'll come back. Let's see. Where are the appendices? Okay, Appendix D. Okay, we don't need to look at the entire appendix here. Maybe we'll cover the appendix in a separate video. I just want to get to the relevant section. Okay, yeah, here we go. Okay, so decimal notation. Oh yeah, so here we go. We have a leading space blank and the leading space showing a minus sign. So that's the difference between positive and negative numbers. The trailing space is there to make sure that two numbers on the same line of the screen will always have at least one space between them, even if you use a semicolon as a print separator. So for here we have an example, print 1, semicolon, -1. There's a trailing space, and then we have the space for the sign. So that's what's accounting for the space, the two extra spaces that we see here. And there's some other examples, like maximum of 10 digits for any number. So really long numbers get elided or converted into scientific notation. Yeah, I think we'll come back and do the appendices in a separate video. Let's go back to where we were in Chapter 3. Covered a lot of ground already. Let's see, we were right here somewhere. Okay, here we are. If the semicolon tells the computer to leave no spaces between variables in a print statement, what happens when we use string variables rather than numeric? Let's try some examples. Okay, let's type in new, get a new instance of TI-Basic. Let a string equal hi there. Hi there. And let b string equal how are you. Okay. Print a string semicolon b string. A string semicolon b string. Okay. And notice that there are now no spaces between these two strings, as we're dealing with string variables, not numeric variables. Oops. The two strings are run together. If we want a space to appear between them, then we must include the space inside one of the sets of quotation marks. For example, let's change a string. So let a string equal hi there, exclamation mark with a space after the exclamation mark and before the end quotes. So let a string equal hi there, space. We're going to end the, oop, I almost forgot to, let's retype this. Hi there. There we go, almost forgot the beginning quotes. So all this is going to do, of course, is replace the value for a string in the computer's memory. Okay. Now let's print a string, semicolon, b string. And because the a string contains that extra space, there's going to be a space between these two words, these two phrases. Hi there, space, how are you? Right here. That's because we included a space right here in the string variable itself. Okay, and that's what we see. Hi there, how are you? So we have our couple of examples here. One without the space, added the space. Here's our second example. Spacing with colons. There is a third quote separator that can be used, the colon. The colon instructs the computer to print the next item at the beginning of the next line. It works the same way with both numeric and string variables. Enter these lines as an example. Let a equal -5, -5. Okay, let b string equal hello. Let c string equal my name is alpha. Print a colon b string colon c string. A colon b string colon c string. Oh, -5. Hello, my name is Alpha. And because my channel's name is CozyAzeroth, we're actually going to do one more little example here. Let c string equal my name is CozyAzeroth. Print a b string colon c string. -5. Hello, my name is CozyAzeroth. To review for a moment, then, these are the three print separators we have used. So the punctuation mark and operation. With a comma prints values in different print zones, maximum of 2 items per line. Semicolon leaves no spaces between items. The spaces that appear between the numbers are results of the built-in display format for numeric quantities. And the colon prints next item on the following line. Okay, the tab function. Besides these separators, there is another method you can use to control the printing on the screen. The tab function operates very much like a typewriter tab key. Print tab 10 semicolon hello. All right, let's get a new instance of TI Basic, which is clear everything from memory. And we'll type print tab 10 in parentheses, then a semicolon and hello. This will be in quotes. So basically, we have moved the printing over 10 spaces. I think if we count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, including the prompting character. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then when it prints the line, it starts printing hello indented 10 spaces. The statement would instruct the computer to begin printing the word hello in the 10th column on the screen. Notice that the quote print line on the screen has 28 columns or character positions, unlike the graphics line, which has a 32 column grid. Thus, the first position on the print line counts as column 1. This is where the P appears in the word print on the previous screen. The last print position on the line is column 28. You can also use the tab function more than once in a print statement. Okay, here we go. Print tab 10. Then semicolon 3, another semicolon I believe, tab 20, then semicolon -4. Notice that the first number 3 is actually printed in column 11 because the preceding or leading space reserved for the sign of the number occupies column 10, just as the minus sign of the second number occupies column 20. The tab function always starts counting in column 1, the leftmost print position on the line, regardless of where or how many times it appears in the print statement. In the example above, the second number, -4, was printed starting in the 20th column on the print line, not 20 spaces from the position in which the first number 3 was printed. So it's 20 spaces from the leftmost line, not 20 spaces from the previously printed item in the line. What happens then if we indicate a column that is already occupied by another message, or if there isn't enough room left on the line to print the message positioned by a tab? Enter this short program to find the answer. Okay, let's check it out. And funny, when I was growing up, this is a section of the book I ignored a little bit because it just wasn't as flashy. I like all the animations and colors, and I still like animations and colors and cool things on the screen. So this might be one of my first times running through all these little programs. Okay, so new 10 call clear 20 let a string equal hello, how are you? Let a string, typos, equal hello, how are you? Let b string equal hi, b string equal hi, with an exclamation mark. 40 print, okay, here we have to be careful, print a string, then we have semicolon, tab 20, then another semicolon. Oh, I'm sorry, I was looking at the wrong line. Tab 5, excuse me. B string. 50 print B string. Then we have tab 20. Semicolon, I think it was a string. Okay, and 60 end. Now run the program. Yeah, let's run it. Okay, so it looks very much like what we have on in the book. Let's analyze it now. In the first example, line 40, column 5 is already taken by the O in hello, so hi starts in column 5 of the next line. And in the second example, let's see here, line 50, the whole message of a string won't fit on any line starting at column 20, so hello, how are you is printed starting in column 1 of the next line. That all makes sense. Notice that separators, semicolons in this case, are also used in the print statement above. Let's try a program to help explore the use of the tab function and separators. Imagine for a few minutes that you are a loyal football fan and it's time for the big game of the season. Since you are also a computer fan and you want to program your computer to cheer the team on to victory, so you enter this program. Let's be careful typing line 30 in there. Let's type new, get a new instance of TI Basic, clear the computer's memory. 10 call clear. 20 let a string equal go. Almost forgot the quotes. Go. 30. Or we'll be careful. Print tab 13. Then I think we had semicolon a string. Okay, then we had two colons. Colon. Tab 12. Colon, team in quotes, semicolon, excuse me, team in quotes. We have two colons, colon. Then we have tab 13. Semicolon, a string. Semicolon, and then we have an exclamation mark in quotes. So semicolon, in quotes, an exclamation mark. And I think that's the rest of line 30. Yes, so we'll hit enter. Enters line 30 into memory. Now looks like we're creating a loop for z equals 1 to 10. For z z equals 1 to 10. 50, prints an empty line. 60, next z. So you can see here that this is basically going to print 10 blank lines. 70 for z equals 1 to 600. Looks like this is a time delay loop. Yep. 80, next z. 90, go to 10. So let's analyze this program. Call clear clears the screen. We're going to have a variable, string variable that just says go. Now we have a complicated print statement on line 3, tab, so that tabs over to the 13th column, prints a string, which is go, tab 12, team. Of course, the spacing is controlled by the semicolons and colons. Then we're going to have another tab over to the 13th position on the line, an exclamation mark. Okay, for z equals 1 to 10, it's going to print 10 blank lines. Then we have a time delay loop, and then go to 10. So it's going to print this line over and over again, separated by 10 lines. Let's see what the book says. Yes, 50 prints an empty line. Note that this is a wraparound line. Yep. Okay. Before you run the program, let's analyze it. Line 10, of course, clears the display screen. Line 20 defines the string variable a string as go. Line 30 is a very, very hard-working line. It might be helpful if we drew a flowchart to describe what's going on here. Tab over to column 13. Do not skip any other spaces. Print go. Print the next print item 2 lines down. That's right, so that's what the colon does. I forgot that knocks it down 2 lines. Tab over to column 12. Do not skip any other spaces. Print team. Print the next item 2 lines down. Tab over to column 13. Do not skip any other spaces. Print go. Do not skip any other spaces. And finally, print an exclamation point. You'll have to admit that it's a lot of information to pack into one program line, even if it is more than one screen line long. The for next loop in lines 40 through 60 will print 10, quote, empty lines to position your message in the middle of the screen. Next, line 70 and 80 form a time delay loop. Then line 90 instructs the computer to go back to line 10 and start all over again. Run the program now and watch your computer cheer. Okay, run. Go team go. Go team go. Go team go. So on and so forth, and this will run until we break the program, which we're going to do right now. The words come on at the bottom of the screen one at a time and scroll up to the center. Then the screen clears and the whole process is repeated until you stop the program by pressing clear. By now your team has probably won the game and you're ready to try some other messages and formats. Experiment for a while with tab and the 3 separators in different print statements before we go on to discuss the arithmetic operations of the computer. I'm not going to bother doing any more experimenting at this point. We've exhausted it. Arithmetic power. You've been introduced before to the arithmetic powers of your computer, but it's time now to take a more detailed, quote, tour of some of its mathematical capabilities. For example, what is the answer to this problem? Remember, the asterisk means multiply to the computer. 4 plus 6 times 5. Okay, kind of a trick question here. Let's say, for example, that the answer represents an amount of money you owe a friend. Your friend argues that you owe him $50 because 4 plus 6 equals 10 and 10 times 5 equals 50. You, however, don't agree. You say you only owe $34 because 6 times 5 equals 30 and 4 plus 30 equals 34. Who is right? Why not ask your computer? Okay, let's do it. Type print 4 plus 6 times 5. Print 4 plus 6. I know the answer. Do you guys know the answer? Times 5. 34. The answer is 34. How about that? You win. Order of operations. There is a commonly accepted order in which arithmetic operations are performed, and your computer performs calculations in that order. In any problem involving addition, subtraction, multiplication, and division, the arithmetic operations will be completed in this way. Multiplications and divisions are performed before additions and subtractions. This is the method your computer used to solve the previous example. It first multiplied 6 times 5 and then added the result to 4, giving you the final answer of 34. Now try this example. Okay, let's type it in. Print 6 plus 15 divided by 3 times 2 minus 4. Let's see what the book says here. Before you press enter, let's think about the way the computer will evaluate this problem. Scanning the problem from left to right, the computer will solve it in this order. 15 divided by 3 equals 5. 5 times 2 equals 10. 6 plus 10 equals 16. And 16 minus 4 equals 12. Your answer then should be 12. Press enter now and see the result. 12. Using parentheses. Suppose, however, that we want the computer to solve the last problem like this. Add 6 and 15, divide the result by 3, multiply that result by 2, subtract 4, giving a final result of 10. We can change the built-in computational order by using parentheses. Try this. Okay, print. What did we have here? We had 6 plus 15. Divided by 3. It was times 2 minus 4. Press enter. We should get 10 on the screen, which we did. The answer 10 is displayed on the screen because the computer has completed the computation inside the parentheses first. So our new order of operations becomes complete everything inside parentheses, complete multiplication and division, and then finally complete addition and subtraction. Oh, hey everyone! Thanks for rating. I'm not sure this is the most exciting stream, but I'm doing some retro computing with this emulator of the Texas Instruments TI-99 4A home computer. The emulator is called Classic 99, and I'm running through this old programming manual called Beginner's Basic for the Texas Instruments TI-99 4A home computer. So hello everyone. Again, feel free to stick around if you find this interesting. We're just doing some retro programming, and we're learning about order of operations, which anyone who's taken mathematics in school, of course, understands the order of operations, but we're learning how this old computer dealt with order of operations. Okay, now try this example. Okay, let's print 8 divided by 2 times 4 divided by 2. Print 8 divided by 2 times, I think it was 4 divided by 2. We'll check our entry here. Print 8 divided by 2 times 4 divided by 2. Okay, let's see what the book says here. The answer is 8 because 8 divided by 2 equals 4. 4 times 4 equals 16. And 16 divided by 2 equals 8. Okay, 8. But suppose we entered the problem with parentheses like this. Okay, so print 8 divided by, I keep tapping back and forth so I can make sure I type everything in correctly. Yes, math's made fun, yes. 8 divided by 2 times 4. You know, I have to say, you know, I first was doing this, I had this computer system, not the emulator, but the original system, and this manual, from the time I was probably 2 or 3 years old, probably 3 years old onward, probably. And I was doing all this stuff when I was 3, 4, 5. It gave me a serious heads up in math, and it was good for me generally. Kids miss out on this kind of thing. I think kids nowadays have to learn this stuff a little too late. Have to lurk for a bit while you eat, but back in a bit, yeah, absolutely. Take your time. We're just chilling, doing some retro programming. I'm running through one chapter at a time, so after I end this chapter, I'll probably end the stream and then come back and do something else in a little bit. In fact, my friend Dylan and I are going to be working on our retro game that we're programming in Pico 8, starting at 4 o'clock. So I will have a little break between this and that, so I'm going to finish this chapter, and then if you happen to notice I'm on later, yeah, please tune back in. That'd be awesome. Okay, so let's finish our entry here. Suppose we enter the problem with parentheses like this. Let's make sure we got it correct. Print. Oh, no, it didn't finish. 8 divided by 2 times 4, and then divided by 2. Okay. This time we get a result of 0.5 because the expression within parentheses has been solved first. 2 times 4 equals 8, 8 divided by 8 equals 1, and 1 divided by 2 equals 0.5. And that is what we get. Here's a slightly harder problem to try. Okay. Print 274 plus 10 divided by 2 times 100 minus 30. Let's enter that in as listed. 274 plus 10. 274 plus 10 divided by 2 times 100. Minus 30. If we enter the problem just like this, we obtain an answer of 744. And we do. That is because, according to the book, 10 divided by 2 equals 5. 5 times 100 equals 500. 274 plus 500 equals 774. And 774 minus 30 equals 744. But by adding parentheses in different places, we can get a variety of answers. Okay, let's do a few different examples here. So print, we've got in parentheses 274 plus 10. 274 plus 10. Then we have divided by 2 times 100 minus 30 in parentheses. Times 100 minus 30 in parentheses. This time we should get 9,940, which we do. And we have a little bubble here to explain why that's the case. First we calculate 274 plus 10, that's 284 inside parentheses. 284 divided by 2 is 142. Then we calculate 100 minus 30 in parentheses, that's 70. 142 times 70 equals 9,940. Let's do the second example. Of course, the point of this might be obvious, but the point of this is to do all the examples in the book here, which I never really did even when I was a kid. I did some of the examples. This is my first time doing every example in this book. Okay, print 274 plus 10. 274 plus 10. Then we get divided by 2 times 100 in parentheses. 2 times 100. And then finally, we get minus 30. Let's see our answer. Negative 28.58. And let's see a rundown of how that works. So 274 plus 10 equals 284. 2 times 100 in parentheses, that's 200. So 284 divided by 200 is 1.42. And 1.42 minus 30 equals negative 28.58. Let's do example number 3. Print. Okay, 274 plus 10 divided by 2, all in parentheses. 274 plus 10 divided by 2. Make sure I got that right. Times 100 minus 30. Outside the parentheses. And we get 27,870. Let's look at why. Okay, so 10 divided by 2, and we're inside parentheses now. 10 divided by 2 is 5. 274 plus 5 is 279 right here. 279 times 100 is 27,900, and minus 30 is 27,870. Experiment. Try the following for practice. Okay, let's enter all these in. Note the differences that parentheses make. Okay, let's do these one at a time. Print 38 plus 6 minus 4. 38 plus 6 minus 4. This is an easy one, of course. 40. 38 plus 6 is 44. Minus 4 is 40. Next example. 38 plus 6 minus 4 times 2. Print 38 plus 6 minus 4 times 2. Did I enter that right? Okay, so we can predict our answer here. We have to do multiplication and division before we do addition and subtraction. So 4 times 2 is 8. So 38 plus 6 is 44. Minus 8 is what? 36. 36. Okay. Next, print. Long expression in parentheses here. 38 plus 6 minus 4. 38 plus 6 minus 4. Finally, times 2. Okay, again, we can kind of predict our answer here. We're going to do what's in parentheses first. So 38 plus 6 is 44, minus 4 is 40, times 2, that should be 80. And it is. Let's do our last example. Print. This one's a little more complicated. We have nested parentheses. So beginning parenthesis. We've got 38 plus 6 minus 4. 38 plus 6 minus 4 in the first set of parentheses, the inner parentheses, times 2 in the outer parentheses. Then we divide that by 6 plus 2. Hope I can do this in my head, we'll see. Don't know what the answer is yet. So let's see if we can figure out the answer here. So we've got 38 plus 6 minus 4, we said that was 40, times 2, so that's 80 in the numerator of the fraction here. So 80 divided by 6 plus 2 is 8, so 80 divided by 8, that should be 10, and it is. Very good. Rearrange the parentheses in the last problem. How is the answer affected? Okay, let's do something totally different here. Let's do, oh, I don't know, 38 plus 6 minus 4 times, let's do something totally different here. We're just kind of rearranging parentheses. Two divided by 6 plus 2. There we go. We answer this totally different here. So 38 plus 6 minus 4, that's 40, times 2 divided by 6, what's 1/3 of 40? 13 1/3 plus 2, so 15 1/3? Yeah, 15 1/3, 15.33333. Repeating, so on and so forth. Okay, scientific notation. So far, all the examples we've tried have given results in a normal decimal display form. However, the computer displays very long numbers, more than 10 digits, in a special way. Try this program. Let's clear the computer's memory. 10, call clear, clears the screen. Oops, not 100, call clear. 20, let A equals 1,000. Or equal 1,000, let A equal 1,000. 30, we're going to start a for next loop for x equals 1 to 5. 40, print A. Okay, 50, let A equal A times 100. We're going to end our for next loop. Next x and 70. Oh, wait, I missed a line? I did. Oh, yep, typo. Got to retype line 50. 50, let A equal A times 100. 60, next x. And finally, 70, end. Since I made a typo, let's list out our program here. Okay, that looks good. So let's think about what this program is going to do. Line 10 is going to clear the screen. 20, it defines a variable. Set A sets it to 1,000. 30 starts a loop, starting with x equals 1, and it's going to loop until x equals 5. Print A. It's going to print that value of A. For the first time through the loop, it's going to be 1,000. Then we're going to multiply A by 100, so 1,000 times 100, 100,000. Next x, that's going to loop us back to line 30, changing the value of x from 1 to 2. It's going to print that new value, 100,000. and then multiply that number by 100 in. So very quickly, these numbers are going to get very large, and we're going to do that 5 times. When you run the program, the first 4 results are printed out in the normal form. The last result, however, looks like this. Okay, let's run it and see. Yep, 1 point e plus 11. This is the system's way of doing scientific notation. We call this special form scientific notation. It's just the computer's way of handling numbers that won't fit into the normal 10-digit space allotted for numbers. 1 point e plus 11 means 1 times, 1 point e plus 11. 1 point e plus 11 means 1 times 10 to the 11th power, or what would that be? And that would be 100 billion. As you can see, 1 point e plus 11 represents a very large number. You'll find a more detailed discussion of the mathematical capabilities and numerical displays of your computer in Appendix D, starting on page 127. Be sure to refer to this appendix when you want to explore the computational powers of the computer. For now, however, let's go on to another very useful feature, the int function, the integer function. So I'm not going to go through the appendix now, but I think I will do the appendices in this book in a subsequent video after I finish all the chapters. Okay, the int function. The int function gets its name from the word integer, meaning a whole number, one that has no fractional part. Integers include 0 and all of the positive and negative numbers that do not have any digits after the decimal point. The best way to learn how the int function works is by trying it. First, let's work a division problem that doesn't result in a whole number. Type print 16 divided by 3 and press enter. The answer is 5.33333333. Print 16 divided by 3. There we go, 5.3 repeating. Now try this example. Print int, I think it was the same thing, 16 divided by 3. Yep, 16 divided by 3. 5. int kept the whole number part of the answer and threw away the digits after the decimal point. Try another example. Print int of 7 divided by 6. Okay. Let's hit enter. That gives us 1. And why do we get 1? Well, 7 divided by 6 is 1.16666 repeating, so on and so forth. So integer of 7 divided by 6 is just 1. It takes the 1, throws away the decimal places. The answer is 1. All of the fractional part has been discarded. How about a real-life problem? Let's say a sales clerk is giving $1.37 in change to a customer. The customer wants as many quarters as possible. How many quarters can be given? So print int of 1.37 divided by 0.25. This will tell you how many quarters will fit inside that $1.37. 5 quarters, right? $1.25, and the rest has to be given out in smaller coins. The answer is 5. 5 quarters can be given. More than one int function can be used in a print statement. Here is an example. Okay, so let's type this. Print int of 1/3. And we have a semicolon. Then we have int integer of 20 divided by 9. Is that everything? I think it is. That'll give us 0 and 2. There we go. And let's see why. So 1/3 is 0.333333. So we ditch the decimal places, and that just gives us 0. 20 divided by 9. What is 20 divided by 9? Let's see. What is 2/9? I'm not sure exactly, but it doesn't matter. Throws away the decimal places and gives us 2. That's why we have a 2 on the screen there. What would happen if you enter these values with the int function? Okay, well, let's see. 8, 8.99, 8.34. Well, we don't even have to do them, but we will try them on the computer and see. So integer of 8 is just 8. Integer of 8.99 is also 8. Integer of 8.34 is also 8. So we should get 8 for all 3 examples. Print int of 8. That's 8, of course. print int of 8.99 also gives us 8, and 8.34. Integer of 8.34, also 8. Oh, and we could, of course, do them on the same line, but we don't need to do that. If you used int with a whole number, integer, you just get the same number back. In the other two examples, no matter what the digits are to the right at the decimal point, the int function truncates or cuts off those digits. That is, it works this way for positive numbers. What happens with negative numbers? We use a program to explore int and negative numbers. Enter these lines. So let's clear the computer's memory. 10, call clear. 20 for a equals 1 to 7. That's the beginning of a for next loop. 30, okay, here's our complicated print statement. Print negative a divided by 3, comma, int of negative a divided by 3. Negative a divided by 3. 40, next a. That's what causes the loop to go back to line 20 and increment the value for a until we reach a equals 7. Next a. And 50 ends the program. Okay, run. Okay, so this is an interesting example. So negative 0.33333 equals negative 1. Negative 0.66666 equals negative 1. Negative 1, of course, just is negative 1. So it basically goes down to the integer immediately below the given values. So this is a weird case. We have negative 1.33333. The integer immediately to the negative of that, to the left of that on the number line, is negative 2. Negative 1.66666. Same thing. What's the integer immediately to the left of that on the number line? Negative 2. So on and so forth. You get the idea, I think. Okay, run the program. The screen will show these results, which it did. So int of x, where x represents a number or a mathematical expression, computes the nearest integer that is less than or equal to x. Perhaps, yeah, I think a number line is the best way to explain this. Perhaps looking at a number line will help to explain. So yeah, any number, so let's take, for example, these negative numbers, anywhere between negative 2 and negative 1. Any of these fractional numbers here, basically, the computer ignores the decimal places and then finds the integer immediately to the left of that, all of which is going to be negative 2. With these right here, negative 3 to negative 2, anything in the middle here, negative 2.6, negative 2.3, anything in between, the computer is going to find the integer immediately to the left of that on the number line, which is negative 3. As you see from the number line, when x has the value of negative 0.3, the nearest integer that is less than or equal to x is negative 1. One last feature associated with int is very useful to know. It can appear on the right side of an equal sign in a let statement. For example, try the next series of lines. Okay? Let a equals integer 4 divided by 3 plus 2. Okay. A equals integer, make sure I type this in right here, 4 divided by 3 plus 2. Did I get that right? I did. So print a. That gives us 3. In the let statement, int of 4 divided by 3 produces the integer result of 1. This result is added to the constant 2, yielding 3 as a final result. A is then assigned the value of 3 and printed. Several applications of the integer function are shown in the chapters that follow. For now, try some other experiments with int so that you become even more familiar with how it works. Okay, let me just do an example here. So print int, let's just do negative, I don't know, some arbitrary number, 27.79. So if that's on a number line, we're going to take, we're going to be to the right of negative 27, a little more positive than the negative 27. And we're going to find the integer immediately to the left of that on the number line, which is just going to be negative 28. So on and so forth. Piece of cake. Summary of Chapter 3. Chapter 3 has introduced you to some new and powerful TI basic abilities. For next, you've used this statement to build controlled loops that repeat a part of the program a specified number of times or create a time delay in the program. Print formats. You've learned how to control the spacing of print items using the 3 separators, comma, semicolon, and colon, and the tab function. Computation. You've discovered that your computer follows a certain order, a certain mathematical order in solving problems. 1. Everything in parentheses is computed first. 2. Multiplication and division are done next. 3. Addition and subtraction are performed last. And the integer function, int function. You learned how this function works on both positive and negative numbers that are not integers or whole numbers. These features will help prepare you for the programs that follow in the next chapters. And that, my friends, is Chapter 3 of Beginner's Basic for the Texas Instruments TI-99 for a home computer. My favorite vintage computer system, the one I had when I was a kid. So I'm going to take a break. I've got to do a couple things before I get ready to do our retro programming stream. We're going to be working on Frieza's Fury, our retro 8-bit style Dragon Ball Z themed fighting game in Pico 8. My friend Dylan and I are going to work on that at 4 o'clock, thereabouts. So be sure to tune back in. Hopefully you're following and or subscribing, getting notifications when I start a new stream. We're going to do that for 2 or 3 hours, try to get a couple new features implemented in our game, and then probably be back later this evening for some World of Warcraft. If you're watching this on Twitch, be sure to check out my YouTube channel as well. You can find me under CozyAzeroth or Zachary Fruling. And also remember to like, subscribe, follow, share, anything you want to do. Same thing on YouTube. If you're watching this on YouTube, also check out my Twitch channel, CozyAzeroth, to catch up my live streams, both for retro programming, World of Warcraft, and any random games I feel like playing, and anything I feel like sharing with the world. I tend to live stream it on Twitch these days. Hope everyone's having a good day, and no matter where you're watching this or when you're watching this, and I will be back shortly with some retro programming, working on a retro video game. Thanks for tuning in, everyone. Thank you for rating Halionics. Really appreciate it. And hello to everyone who's joining me for the first time and or not the first time. Nice to meet everyone who is new to the channel. Try to come back. We do some interesting stuff around here. Hope everyone's having a good day. I'll see everyone in half an hour, give or take. Take care now.